So in this video, I'm going to discuss collisions. Collisions, in a previous video, I said that in a collision, if you put all the particles that's colliding with each other in the same system, then although you may have some kind of external force applied, like such as a friction force or something, but those collision force, the interactive force, is so large that you can ignore friction force and treat the system as an isolated system. Then you can apply conservation of momentum if you consider all the particles that's making a collision in one system. So in this video, I'm going to talk about more about collisions. So collisions, you can apply conservation of momentum, treat the system as being isolated. There is two kinds of collisions. So, okay, collision. So again, you can always apply conservation of momentum for collision. Conservation of momentum, total momentum. Then there's two kinds of collision. One is called elastic collision. And the other one is called inelastic collision. Either way, it's a collision, so you can apply conservation of momentum. But what's different for the elastic collision and then inelastic collision is, let's see, elastic collision is not only the total momentum, and so here we haven't discussed this, but kinetic energy. Both kinetic energy and the total momentum is conserved, unchanged before the collision, before and after the collision. What does it mean? When you can, so we know that any collision have a total momentum is conserved and the kinetic energy is conserved. So what it means is like very good example is like a billiard. Balls, right? They come together, make those billiard balls come together, and then they make a collision, and then they move. And this collision is an elastic collision. You can treat it as an elastic collision. There is no deformation, no shape deformation. And there is no generation of heat. So therefore, there is nothing that's lost in a collision. You don't use the energy to change the shape of the object. You have no heat generated. And it's a perfect collision, nice clean collision. That's called elastic collision. And you might understand better once we also introduce the kinetic energy. So like a billiard ball that makes a nice collision. It's technically though, there's no such a thing that's a real elastic collision. And but I hope you see that. Then therefore, inelastic collision is everything else. Everything else is the inelastic collision. That you might still see, you may see, yes, shape deformation. Maybe you might have a heat generation. Kinetic energy is not conserved. Energy is used to do some kind of a work. However, since it's collision, because it's a collision, right? That means still total momentum is unchanged. So the momentum before the collision and after the collision, it still stays the same. But you may lose some kind of energy because you may see a shape deformation, you may see heat generation. So that's the inelastic collision. Elastic collision is a nice collision that you don't lose energy, no, you don't see any shape deformation and no generation of a heat. Like a billiard ball that's colliding is a good example of elastic collision. There is something for the inelastic collision. There is something that's called perfectly inelastic collision. So this is perfectly inelastic collision. What does it mean for the perfectly inelastic collision? Is that objects stick together after the collision. So before the collision, they're coming together. This is before. And then they'll collide. And then after the collision, they get smooshed. So they may share the same, they're gonna share the same velocity. You might have a V1, V2, but they collide and becomes M1 plus M2, become one object. After. So whenever the objects gets together and smoosh, that's called perfectly inelastic collision. Let me show some example. Here, if I need to show the voice. All right. Okay, so it's zeroed, 48 gram. 60 gram. So this object have a 60 gram. And then let's see, we're gonna have another object. Okay, so this is 0 gram. This one. So this one 60 gram by itself is another 60 gram, right? And here you're gonna see these train toy have a magnet. All right, so in this train toy, there are magnets in it. And right now, if I put it closer, you see it's repulsive on this side. But if I put it on this side, it sticks. So this is attractive.
It's ready.
So if it's repulsive, they don't, when they collide, they make a nice collision that's elastic collision. And then when they stick together, what kind of a collision is that? Let's see the example. Magnet is switched. It's gonna make elastic collision. Or this one, I guess. Another example. Elastic collision. Same mass, one with the initial speed, the other at rest. Right? What happens? Okay. So okay, if for elastic collision, predict what's going to happen. If one object, they're both two objects, they're both the same mass, right? And then one is at rest, the other one is moving with some initial speed. What happens to their speed after the collision? Initial speed, the other at rest. All right, and then here is the, I switched the side of the magnet. And guess, if I switch the side, so now it's attractive force. What kind of a collision is that? How do you call that collision? Totally inelastic collision. This is gonna collide. Moves together. All right, so now predict their final velocity. One is, they're two the same mass, right? Same mass, another one comes over with the same velocity, and then they make a collision and move together. After the collision, what do you say their final speed compared to their initial speed of the one object? Okay. Totally inelastic collision. All right. And finally, I want to talk about one more thing. Good. So this is perfectly inelastic collision, which means that two objects collide. After that, they move together. Then no kinetic energy is not conserved, but still because it's collision, you're gonna still see the P1, the total momentum before the collision is still equals to the total momentum after the collision. So M1 V1 plus M2 V2 is equals to M1 plus M2 of the V prime, the new velocity after the collision. And like I said, this kind of a conservation thing, what you can do is to take a picture. So before the collision, you take a picture, find out the total momentum. This object is moving with this mass object is moving with this velocity. This mass object is moving with this velocity. You write that down, find out the total momentum. Then you take another picture after the collision and compare the total momentum before and after. It should be unchanged. So how about this? If we were to look at this process backward, let's see this as a backward. What do you see? If we see this process as backward, then we're going to have a one big object, which is M1 plus M2. That's going to be doing something. Then it's going to be moving with a different velocity with the smaller pieces. And this is called, this is called explosion. Right? It's the one object and it splits apart. So explosion is just a time reverse, but you still see the same thing happening. Explosion, also the interactive force between the object is so large that you can apply conservation of momentum if you put all the particles in the same system. So you can treat the explosion similarly to perfectly inelastic collision. All right. And you can apply also total momentum is conserved, unchanged before the explosion to the after the explosion. All right, so this is going to be the end of this video. I'll see you in the class.